Hey everyone, welcome back to the deep dive. We've got a really interesting one lined up for you all today, and big shout out to at Pranovoke8189 for this one.
Yeah, thanks for the suggestion at Pranovoke 8189. This is right up our alley.
It really is, and
Yeah.
we talk a lot about AI and all the advancements, and this one, I think this is going to be a good one. So today we're going to be looking at how AI models can remember things better, basically. And not just like small bits of info, but how they can learn from huge amounts of data.
Exactly. And that's something that, AI researchers have been working on for quite a while now. And this new research is it's really intriguing. It's called Titans.
Titans, yeah.
Yeah.
It sounds pretty epic, right?
It does have a certain ring to it, and that's what we're going to be diving into today. The core ideas behind this new architecture.
Right. And our main source for this deep dive is going to be the research paper itself, Titans, Learning to Memorize at Test Time.
Yeah, that title alone kind of gives you a hint of what they're going for here. It's not just about storing information, but actually using that memory effectively during the testing phase when the AI is actually trying to solve a problem.
Okay, so let's set the stage here. The paper starts by talking about the current state of things in the world of sequence models. And anyone who's been following AI knows that transformers are the big players right now.
Absolutely. Transformers have been absolutely revolutionary for natural language processing and really understanding how sequences of data work, but they do have their limitations.
Right, and one of the big ones that the paper highlights is how transformers handle those really long sequences of data. Like imagine trying to feed an AI an entire book or a massive data set.
Yeah, that's where things start to get tricky for transformers. They're really good at capturing those direct relationships within a certain window of information. But when you try to scale that up to ridiculously long sequences, the computational cost just explodes. It's what they call quadratic complexity, meaning the resources needed grow much faster than the length of the data.
Yeah, it's like if you try to remember every single detail of a movie you watched a month ago. You might remember the main plot points, but all those little details, those nuances, they start to fade.
And that's kind of what happens with transformers. They can lose track of those crucial details when the context gets too big. Now, there have been attempts to address this. Like linear transformers, they're designed to be more efficient with longer sequences.
But the paper suggests that there might be a trade-off there, right? Like you gain efficiency, but potentially lose some of the richness and the understanding.
Exactly. That's the core issue. Linear transformers gain their efficiency by essentially compressing the information into a fixed-size representation. It's like trying to summarize a whole novel in a single sentence. You might capture the gist, but you're definitely missing a lot of the depth and the subtleties.
Right. And that loss of detail can lead to a drop in performance on certain tasks. So the researchers are arguing that maybe we're missing something fundamental here. If we look at how our own brains work, we have different types of memory, right? Short term for what we're immediately focused on, and long term for things we've learned over time.
That's a really key point, and it's something that the paper emphasizes. A lot of existing AI architectures don't really have that distinction between different types of memory. They try to cram everything into one system, which might not be the most efficient or effective way to do it.
And that brings us to the heart of what Titans is all about, this brand new neural long-term memory module. It's not just a tweak to an existing model. It's a whole new component designed specifically to address this challenge of long-term memory in AI.
Right. And the key idea here is that this module actually learns how to memorize historical context during the testing phase. So it's not just passively storing information, it's actively figuring out what's important and what needs to be remembered.
And they do this using a really interesting concept called surprise. Basically, the idea is that events or pieces of information that are unexpected are more likely to be memorable.
It's very intuitive when you think about it. In our own lives, we tend to remember things that stood out, that surprised us, or violated our expectations. Titans tries to replicate this by actually measuring surprise using the gradient of the neural network.
Okay, hold on, gradients. Now that's getting a little bit technical. Can you break that down for us?
Sure. So the gradient essentially tells you how much the output of the neural network changes with respect to a small change in the input. In this case, a larger gradient means that the current input is more unexpected or surprising to the model.
So it's like if you're reading a book and suddenly there's a plot twist that completely catches you off guard, that's going to stick with you more than just the normal flow of the story.
Exactly. And Titans uses these gradients to identify those high surprise events and make sure they get stored in long-term memory.
But the researchers also realized that just focusing on immediate surprise could be a problem. You might miss important information that comes right after the surprising event.
Right. It's like if you get so fixated on that plot twist that you miss some crucial details that explain what's really going on. So to address this, they incorporated a past surprise component.
Past surprise.
Yeah.
So it's like having a lingering memory of the surprise, even as the model moves on to new information.
Precisely. It helps maintain that focus even after the initial shock has worn off. And they actually compare this to the concept of momentum in gradient descent, which is a technique used to smooth out the learning process in AI.
Okay, I'm seeing some connections here to some pretty fundamental concepts in machine learning. It's not just about memory, it's about how that memory is learned and updated.
Exactly. And that's one of the things that makes this research so interesting. They're drawing on these well-established ideas from optimization theory and applying them to the problem of memory formation.
So we've got surprise. We've got past surprise. But obviously you can't remember everything forever, especially when you're dealing with these massive amounts of data. So how does Titans manage that?
That's where the surprise decay mechanism comes in. That feeling of surprise naturally fades over time, and Titans models this by having the surprise gradually diminish as the model processes more information.
So it's like how the memory of that plot twist might become less vivid over time. But it's not just a random fading. It's actually influenced by the data itself.
Right. It's a data-dependent decay, which means it adapts to the specific characteristics of the information the model is processing. And they actually connect this back to forgetting mechanisms in other types of neural networks, like recurrent neural networks or RNNs.
So it's like they've taken inspiration from different areas of AI research and combined them in a really clever way to create this sophisticated memory system.
Absolutely. And one of the most fascinating parts for me is that they show how this whole surprise mechanism is mathematically equivalent to optimizing a metaneural network using techniques like mini batch gradient descent momentum and weight decay.
Okay, now you're just showing off with the technical jargon, but seriously, that's a really deep connection to some core principles of machine learning.
It is, and it highlights how they've managed to bridge these different areas of AI research in a really elegant way.
Okay, so we've talked a lot about how Titans remembers things, but what about actually using that information? When the model needs to access its long-term memory, how does that work?
The retrieval process is actually quite straightforward. It happens through a standard forward pass, which is essentially just running the information through the network without changing the weights of the memory module. It's like looking up something in a database. You access the information without modifying the database itself.
That makes sense. But we're talking about potentially huge amounts of data here.
Yeah.
So efficiently training this long-term memory module must be a challenge.
Absolutely. But the paper highlights how they can leverage techniques like matrix multiplications and tensorizing mini-batch gradient descent to parallelize the training process.
Okay, now you've lost me again. What does all that mean in plain English?
Basically, it means they can break down the training into smaller independent chunks that can be processed simultaneously on specialized hardware like GPUs or TPUs. So instead of training on one massive data set all at once, they can distribute the workload, which makes it much faster and more efficient.
So it's like having a team of workers instead of just one person trying to do everything themselves.
Exactly. And that's crucial when you're dealing with the scale of data that Titans is designed to handle.
Now, in addition to this dynamic long-term memory, Titans also incorporates something called persistent memory, which sounds like a different kind of knowledge altogether.
It is. Persistent memory refers to parameters within the model that are learnable, but they're not dependent on the specific input sequence they're processing. So it's more like general knowledge about the task at hand.
So it's like having a foundational understanding of the world even before you start learning specific details.
Exactly. And the paper gives a few reasons why this persistent memory is important. First, it provides that baseline knowledge that's independent of the specific context. Second, it's similar to the feed-forward layers in transformers, which also have these learnable data-independent parameters. And finally, they suggest it might help to mitigate a potential bias in attention mechanisms towards the earlier parts of a sequence.
So it's like having both a textbook of general knowledge and a notebook for jotting down specific details from a lecture. You need both to really understand the material.
That's a great analogy. And the researchers didn't just create one version of Titans, they actually experimented with 3 different architectures, each with a slightly different way of integrating this long-term memory module.
Right. Let's dive into those. The first one is memory as a context, or MA.
In MMAC, the information from the long-term memory is essentially combined with the persistent memory and the current input segment. And then this combined chunk of information is fed into the attention mechanism. So the attention mechanism can decide which parts of the memory are relevant and what new information should be stored.
So it's like the attention mechanism is acting as a filter or a gatekeeper, deciding what gets through to the main processing pathway.
Exactly. And the second variant is called gated memory, or MAG.
This one sounds like the long-term memory has a more direct influence on the processing.
You got it. In MAG, the long-term memory is updated directly from the input, and its output is then combined with the output of a sliding window attention mechanism using a gating mechanism. So instead of being directly part of the context for attention, its influence is regulated by this gate.
So it's like the long-term memory has its own channel, and the gate controls how much information flows through.
Exactly. And the third variant is memory as a layer, or MEL.
And this one sounds like the long-term memory acts as a separate processing step.
Exactly. In ML, the input is first processed by the long-term memory module, and then the output of that is fed into the attention mechanism. So it's like the long-term memory is pre-processing the information before it reaches the attention mechanism.
It's really interesting to see these different approaches to integrating long-term memory. It shows that there's no one-size-fits-all solution, and there's still a lot of room for innovation in this area.
Absolutely. And now the big question, how well does Titans actually perform? The paper presents a whole range of experimental results across a variety of tasks.
Right. They tested it on everything from language modeling to common sense reasoning to these really challenging recall tasks they called needle in a haystack, where the model has to find a single piece of relevant information buried in a ton of irrelevant data.
They also tested it on genomics data and time series forecasting, which shows just how versatile this architecture can be.
And the results were pretty impressive, right?
Yeah, they were. On many of the benchmarks they tested, Titans outperformed both modern recurrent models and hybrid models that combine recurrent and attention mechanisms.
And how did it compare to transformers, which are kind of the gold standard in many AI tasks right now?
Well, that's where things get really interesting. Titans actually showed competitive or even better performance than transformers, particularly when they scaled up the context window to those really long sequences.
So it was able to handle those massive amounts of data that would normally choke a transformer.
Exactly. And in those needle in a haystack tasks, the neural memory module on its own actually performed surprisingly well. They attribute this to its ability to manage memory effectively using those surprise and forgetting mechanisms we talked about earlier.
So it was able to sift through all that data and hold on to the one crucial piece of information.
Exactly. And on this benchmark called Babylon, which is specifically designed to test reasoning over very long documents, Titans, specifically the M+C variant, actually outperformed even massive models like GPT-4, and it did so with significantly fewer parameters.
So it was both more effective and more efficient.
Exactly. And they also did what are called ablation studies, where they systematically removed different parts of the architecture to see how each component contributed to the overall performance.
So it's like taking apart a machine to figure out how each piece works.
Exactly. And they found that almost all of the components, they tested the deep memory, the convolution, the momentum, the weight decay, and the persistent memory, they all played a positive role in the model's success.
So it's not just one magic bullet. It's the combination of all these different elements working together that makes Titan so effective.
Exactly. And they also found that increasing the depth of the long-term memory module generally led to better performance, especially on those longer sequences. But this did come with a trade-off in terms of training speed.
So it's a balancing act between capacity and efficiency.
Exactly. And they also saw strong performance in time series forecasting, where the neural memory module outperformed other state-of-the-art models. And even in DNA modeling, Titans achieved competitive results on genomics benchmarks.
So it really seems like this architecture has potential across a wide range of applications.
Absolutely. And finally, when they looked at the efficiency of Titans in terms of training speed, they found that the ML variant could achieve better throughput due to its compatibility with techniques like flash attention.
So it's not just about performance, it's also about making these models more practical to train and deploy.
Exactly. So to sum it all up, Titans represents a really exciting new direction in how we approach long-term memory in AI. It's a fundamentally different approach that takes inspiration from how human memory works and offers significant advantages over existing models.
It's really pushing the boundaries of what AI can do, especially when it comes to processing those massive amounts of data that are becoming more and more common in the real world.
Absolutely. And the modular design with its separate short-term and long-term memory components, along with this concept of learning to memorize at test time, it opens up so many possibilities for future research.
It really makes you think about what other aspects of human memory and learning we can incorporate into AI to make it even more powerful and effective.
Right. It's not just about remembering facts. It's about understanding context, making connections, and learning from experience.
And that's what makes this research so compelling. It's not just about building bigger and faster models.
Yeah.
It's about building smarter models that can truly learn and reason like we do.
It's an exciting time to be in AI, and research like this is really pushing us towards a future where AI can truly augment and enhance our own cognitive abilities.
Well said. And that's going to wrap it up for this deep dive into Titans. A huge thank you again to @Pranovoke8189 for bringing this paper to our attention.
Yeah, thanks again for the recommendation at Pranovoke 8189. It was a great pick. And as always, we encourage you all to check out the paper yourself and let us know what you think.
And be sure to subscribe to the channel and hit that notification bell so you don't miss out on any of our future deep dives. Until next time, stay curious.
Keep exploring.